Hello everyone, and welcome back to another episode of the Internet Computer Developer Journey. In today's episode, we are starting the final section of our developer journey. So we are entering level 5. So this is the final of 6 levels in this developer journey. And that means that we are in the home stretch. This section is focused on sample applications and taking a look at some of the more advanced features of ICP. So far we've taken a look at most of the core components of the Internet Computer Protocol and some example applications on how you can use them. But in this final section, we're going to take a look at sample applications that either use one of the advanced features of ICP or they combine multiple features into one comprehensive application. So in today's episode 5.1, Developing an Encrypted Notes dapp with vetKeys, we're going to be taking a look at the on-chain encryption feature on ICP known as vetKeys. And before we get started, it is important to note that vetKeys is still in the testing and experimental phase. At the time of this video's recording and at the time that this example project has been published, the vetKeys API is not ready for production environments, so it is highly recommended to only use these for proof of concept and not use them in a production environment until the API is officially launched and released. But nevertheless, we're going to take a look at what makes vetKeys an extremely powerful upcoming feature of ICP. So when you're building an application, many instances will require that you need a secure way to store user data or other private application data and keep certain aspects of the application private. On a blockchain, transactions are traditionally public, and therefore dapps might rely on storage within a web browser to store user-side secrets, and this can lead to potential security vulnerabilities. On ICP, the vetKeys feature is designed to give developers options for more enhanced privacy, encryption, threshold decryption, and security capabilities when building projects and applications. The goal of this feature is to allow developers to retrieve encrypted information from external locations and share it with different users in a private and secure manner. So in this tutorial sample, we're going to take a look at how vetKeys can be used to encrypt the application's data, and we'll do that in the form of having notes that a user can create, such as a grocery list or whatever note content they'd like to save, and then that note data will be encrypted with vetKeys. So before we get started, let's get some context on what vetKeys are and some of the motivations and design choices around the vetKeys feature. So the term vetKeys is short for verifiably encrypted threshold keys. This feature enables several cryptographic functionalities on ICP and has a strong design focus on facilitating on-chain encryption, data privacy, and data security. From a high level, the main objective of vetKeys is to provide a threshold key derivation interface to allow canisters to obtain encrypted threshold signatures and to allow for symmetric encryption for public key or identity-based encryption. To understand vetKeys, first let's cover a few of the fundamental cryptographic concepts and some of their disadvantages that vetKeys strives to solve. So in cryptography, most tools are built from what are known as crypto primitives. A crypto primitive is a core building block that is used with its existing functionality, or it can be used to build other more complex cryptographic protocols and tools. Some examples of crypto primitives are block ciphers such as AES, hash functions such as SHA-3, or signature schemes such as ECDSA. The vetKeys feature introduces a new primitive, vetKD, which extends the functionality of a primitive known as identity-based encryption, or IBE. vetKD, or verifiably encrypted threshold key derivation, allows encrypted data's decryption keys to be derived on demand. Public key encryption, or PKE, is a commonly used form of encryption that allows for data to be communicated confidently over a public channel by encrypting the data messages. For example, if one user wants to send an encrypted message to a second user, the PKE scheme might use steps such as user 2 is going to generate a public and private key pair using a key generation algorithm. Then they're going to publish the public key from that key pair online somewhere, such as within a public key infrastructure. The first user can retrieve that second user's public key, then use it to encrypt a plain text message that they're going to send back to user 2. This is going to result in a ciphertext, which is the encrypted plain text of a message after it is processed by an encryption algorithm. And then the first user can go ahead and send that ciphertext to the second user. And the second user can decrypt that using their private key and the decryption algorithm. And in the end, they are going to see the decrypted plain text message that user 1 originally sent them. In PKE, it is a standard practice to store a public key on a trusted public key infrastructure and securely manage the private key in a separate instance. PKE can get complicated and difficult quickly, though, resulting in developers being discouraged to use cryptography in their applications. vetKeys strives to make this aspect of cryptography easier for developers. Moving on to identity-based encryption, or IBE. IBE is designed to address some of the pitfalls of PKE, as it allows for an arbitrary identifier string or identity to be used as a public key that is then used to derive the private key. To compare IBE to PKE, consider this scenario. In an IBE scheme, there must be a trusted key deriver, or KD, that is used to run the IBE key generation algorithm and generate a master key pair that contains the private and public key based on the identity that was provided. Then the first user can run the IBE encryption algorithm to encrypt a plain text message to the second user using that second user's identity, and that's going to result in the ciphertext that is sent to user 2. User 2 authenticates to the KD with their identity and requests the private key that corresponds to their identity, which the KD will return to them. And then the second user, with their newly obtained private key, can use that to decrypt the ciphertext sent from the first user. So one important note about IBE is that it requires a central authority, in this instance the KD, to derive the decryption key. This can be a problem for working with decentralized technologies that do not want to place trust in a centralized authority. And so this is another pitfall that vetKeys strives to address. So within the vetKeys feature, the core piece is the key derivation primitive, or vetkd. The key derivation capabilities provided by vetkd are designed to provide key derivation without relying on a central authority by distributing the trust among multiple parties, then requiring that a minimum threshold of all parties collaborate to derive the private key. To do this, first a distributed key generation, or DKG, protocol is used to create a master key that is distributed amongst multiple parties, where each party holds a share of the master key. Later, when a user wants to derive a decryption key, or a vet key, based on their identity, a threshold of nodes derive the user's vet key from the user's identity and the shares of the master key that they hold. So going back to a simple encrypted message scenario, if we compare this to the other two examples with PKE and IBE, in the vetkd scenario, nodes in the network are going to participate in the DKG process to obtain shares of a master secret key and a master public key. Each node may hold a number of shares, but no node may hold the majority amount of key shares. User 1 is going to encrypt their message under user 2's identity and the master public key, and then they're going to send the resulting ciphertext to user 2. When the second user wants to decrypt their message, they must authenticate their identity to ICP to retrieve their vet key to decrypt the ciphertext sent by the first user. They start by using a transport key generation, or TKG, algorithm to generate a transport public and private key pair. User 2 then sends the transport public key along with their request to authenticate their identity and derive a vet key. The transport public key gives the network a way to send user 2 encrypted responses. And so if we go back to what vetkey stands for, this is the E in vetkd. Once the second user has been authenticated, the nodes that use the DKG algorithm are going to derive user 2's vet key using the node's master key shares. Then they're going to encrypt that using user 2's transport public key. Anyone can use an encryption key share algorithm to verify that the encrypted key contains a legitimate decryption share. This is the V in vetKD. The network's nodes can also combine the encrypted shares to produce the full vet key for the identity. And then finally, user 2 is going to decrypt the message with their transport private key, which reveals the vet key corresponding to their identity. And then lastly, the second user is going to receive a recovery algorithm that allows them to decrypt the response with their transport private key, and that's going to reveal the vet key corresponding to their identity, which they can then use to decrypt the message sent by user 1. It's important to note that this allows users to retrieve decryption keys or vet keys from any device at any time, overcoming one of the core pain points of public key encryption. Vet keys are made possible by leveraging the extremely useful properties of BLS signatures. So a quick overview of BLS signatures. These are a digital type of signature introduced in the early 2000s. They are widely used across ICP because they are short, unique, easy to port into a distributed setting, and are fast to compute. They use 3 algorithms: a key generation algorithm that may or may not be distributed, a signing algorithm, and a verification algorithm. In a threshold setting, BLS signatures include a 4th combination algorithm. To demonstrate how BLS signatures are used on ICP, we can take a look at a similar scenario for validating that a message sent from an end user has been sent from ICP. So nodes on the network participate in the DKG process and obtain private key shares. Each node computes a signature share for a message using its share of the signing key. The nodes use the combination algorithm to combine the signature shares and produce a single signature that's sent to user 1. And user 1 can use a verification algorithm to check whether the signature that was sent uses the public key of ICP, validating that it was signed by the nodes running on ICP. In the scenario of vetKD, the master key of the IBE scheme uses a BLS signature key secret that is shared amongst the nodes. The derived identity is threshold signed, resulting in a signature that acts in a symmetric encryption key. Each of these components of vetKeys are described in the vetKeys primer. So now let's take a look at the vetKeys example app. So in this sample application, we are going to create a notes app that allows us to create a note and encrypt it using vetKeys. Each note is going to be encrypted with an AES key that is derived from a principal-specific vet key that the backend canister is going to obtain using the vetKD system API. And so this is going to eliminate any need for device management within the application. And just as a reminder, this example includes the proposed vetKD system API. This is an insecure implementation and should not be used in production or for encrypting any sensitive data. This example is for demonstration purposes only. So before we get started, verify that you have set up your developer environment according to the instructions in 0.3 Developer Environment Setup. Then go ahead and open a new terminal window and navigate into whatever your working directory is for the sample applications that we have used so far in this developer journey series. And if you need to clone the examples repo again, go ahead and run the git clone command. And then we're going to navigate into the examples directory, and we want the Motoko subdirectory, and we want the folder specifically for the encrypted notes dapp vetkey or vetKD. And it's important to note that there is another project in this directory just called encrypted notes dapp that does not use vetKD, so make sure that you are in the vetKD version. And a Rust variation of this project does exist in the corresponding Rust subdirectory. So to set up this project, since there are two variants of it, a Motoko version and a Rust version, we do have to set a local environment variable to equal Motoko. So we're going to do export build underscore env and then equal Motoko, and we have Motoko in all lowercase. This example also includes a pre-deploy script, which is used to generate some files that are specific to whatever build environment variable we've set. So in this case, it's going to generate the build files for the Motoko variation. So we're going to go ahead and run that. So sh and then pre-deploy.sh. And we're going to see it's going to generate the dfx.json file and then some other TypeScript and JavaScript files for specifically the front end. And then we want to run npm install to install all of the necessary packages for the front end of this application. Now, if we take a look at this project's files, let's open VS Code, and I already have it open to my examples folder, but I'm going to navigate to Motoko and then encrypted notes dapp vetkd. And then let's take a look at the dfx.json file. So just making this a bit bigger. So we can see that we have a couple of different canisters defined here. First, we have the vetKeys system API. This is using a Candid and Wasm module that are stored locally in the project's directory. These are files that reflect the proposed vetKeys system API that is not currently released on the mainnet. It's still in testing and experiment phase. So for now, we just have local versions of the Candid and Wasm files for this canister, rather than pulling it from the mainnet like we do for Internet Identity or the EVM RPC canister. Next, we have the encrypted notes Motoko canister. So this is going to be our backend canister. It has a dependency on the vetKeys system API canister. And the main file for this is going to be the main.mo file stored in the traditional backend location. So source, backend canister name, which in this instance is encrypted notes Motoko, and then that main.mo file. And this project's files also include by default the variation for Rust, and so we'll see that we have the definition for the encrypted notes Rust canister as well, but we won't be using that in this tutorial. And then we have a canister called www. This is our front end canister. It's going to host the user interface that's going to allow us to create and save encrypted notes. It has a dependency on the backend canister and the system API canister, and it's going to have its entry point at the index.html file. And then lastly, we have the Internet Identity canister. This one is going to be pulled from the files stored on the Internet Identity GitHub. And so it's going to pull those files when we want to deploy that canister. These Candid and Wasm files are not stored locally, whereas the vetKeys system API files are stored locally. So next we're going to look at the code file for our backend canister, which contains the core functionality for our app. And this code has been annotated to explain the program's functionality. It's important to note that the backend canister does not perform any encryption, since it assumes that the notes are encrypted end-to-end by the front end on the client side. So if we go ahead and open this file in VS Code so we can take a look at the comments, we're going to go to source, encrypted notes Motoko, and then main.mo. So first, looking at this code, we are going to have lots of import statements that import different packages and libraries from the base library. Then we are going to define our shared actor class, and we are going to bind the caller and the initializer within this actor class. So at the current recording time of this tutorial, a single canister smart contract is limited to 4 GB of heap size. And so we want to ensure that our canister does not exceed that limit. Therefore, this code includes various restrictions, such as max number of users, that prevent this application from using memory above 2 GB. This is a standard calculation since you should assume that 2x memory may be needed for data serialization during canister upgrades. So in this example, this is sufficient since this is just a proof of concept application, but in production environments, the actual memory usage may be calculated or monitored and various restrictions adopted accordingly. So here we're going to define the app's limits. We are going to have max amount of users equal 500, max amount of notes per user is 200. A note can have 1,000 characters, and the shares per note are going to be set to 50. We are also going to define the type principal as data type text and the note ID as data type nat. Then we're going to define a few public types. First is a type of encrypted note. And remember, this canister does not perform any encryption. We are assuming that the notes are encrypted end-to-end by the front end. So here, the public type encrypted note is going to have encrypted text of type text and ID of type nat. It's going to have owner of principal name, and then it's going to have a list of users that also is set to type principal name. And this list of users is the principal with which the note is shared, and it does not include the owner of the note. Next, we're going to define private fields. Stable actor fields are automatically retained across canister upgrades, and you can learn more about canister upgrades in the Motoko documentation or in the previous developer journey levels. In the sample application, there is a design choice to use globally unique note identifiers for all users. And so here we are defining the private stable variable next note ID equals data type nat, and then we are setting it to be equal to 1. And then we want to store the notes by their ID so that note-specific encryption keys can be derived. So we are defining private variable notes by ID equal map.hashmap note ID encrypted note, and then nat.equal hash.hash. We also want to store which note IDs are owned by different principals. So we want to create private variable note IDs by owner, and then we're going to use another hashmap function to store that. And then lastly, we want to store which notes are shared with particular principals. This does not include the owner, as that is tracked by the previous variable note IDs by owner. So this is going to be note IDs by user, and is going to use a similar hashmap function. So in this example, we are going to use the stable memory as a buffer to preserve data across canister upgrades. Accessing heap data is more efficient, but stable memory is currently higher than heap memory, so you can store more data in stable memory than in heap memory. And so we are going to then define stable variations of each of these variables. So we are going to have private stable var, and then stable notes by ID, and then it's going to define the note ID and the encrypted note. And then we are going to do the same for the stable variables note IDs by owner and note IDs by user. Then we are going to use a utility function to help writing assertion-driven code more concisely. So this is a private function that uses a switch case statement to do that assertion-driven code. Then we are defining a private function called isAuthorized, and it's checking to see if a user is authorized, if it is either the note owner or if it is in the list of users that are added to a note through that note share function. And then here we have a simple public whoami function that just returns the principal back to the caller. Next, we have some shared functions. So these are accessible to remote callers, meaning that anyone can call these functions. And so these are going to add an empty note for the caller and return an ID of a new empty note. And this function is designed to trap if the caller is anonymous, trap if the caller already has the maximum amount of notes, or if this is the first note for the caller and max users is exceeded. And so we are defining this public shared function create note. We are asserting that the principal is not anonymous, and then we are defining the owner of the note as principal.toText and using the caller principal. Then we are defining a new note variable using the encrypted note type, and this is going to have ID of next note ID. Encrypted text is currently empty. When the note is first created, the owner is equal to the owner variable we set above, and then the list of users that this note is shared with is currently empty by default. And then we are using this switch case statement to determine if the user is creating a new note and they already have the maximum amount of notes, and if so, it will trap. And then if they don't have the maximum amount of notes, but if they are a new user and they are creating their first note, it also checks to make sure that the max amount of application users is not exceeded, and if it is, it will trap. And then if all of that is good, it will create that new note, it will make the next note ID increase by 1, and then it will return that new note ID. Then this next function returns the future of a caller's notes. And so this method is declared as an update call rather than a query. While queries are significantly faster than upgrades, they are not certified by ICP. Therefore, we avoid using queries throughout this sample application, ensuring that the result of our functions go through consensus. Otherwise, this function could omit some notes if it got executed by a malicious node. So this function is going to return an array of encrypted notes, and it's going to trap if the caller is anonymous. So it's going to define this getNotes function. It's going to use that same logic to assert that the caller is not anonymous and set the caller as user. And then it's going to use a list function to define the owned notes variable. And then it's also going to define a shared notes list as well. Then the update note function is defined. This replaces the encrypted text of a note with ID value ID, and it's going to update that with the encrypted text. And it is going to trap if the caller is anonymous, trap if the note with ID value ID does not exist. It will also trap if the caller is not the note's owner and not a user with whom the note is shared, or if encrypted text exceeds the maximum characters, which we set to 1,000. So we're going to use that same authentication logic to identify the principal. Then we're going to get the note by its ID, and if that ID does not exist, the function is going to trap with not found, or if the caller is not authorized to see that note, it's going to trap with unauthorized. And then lastly, it's going to check to make sure that the note size is within the maximum amount of characters limit. Then next, we are going to define a function that shares the note with note ID with a user. It has no effect if the note is already shared with the user, and it's going to return a future of the unit, and it's going to trap if the caller is anonymous, if the note ID does not exist, or if the caller is not the note's owner. So here's this public shared function called addUser. It's going to do that same caller identification function. Then it's going to get the note by its ID, and it's also going to trap using that same logic as the previous function for if the note ID is not found or if the caller is unauthorized. And then it's going to assert note.users.size and make sure that we are not exceeding the maximum amount of shares per note. And then if that is not currently exceeded, it's going to use this if statement to go through and add the user to the list of principals that the note is shared with. And then it's going to use a switch case statement to validate that the note has been added to that shared user's list of notes. Then we're also going to define a function to unshare a note ID with a user, and it is going to use the same error handling where it will trap if the caller is anonymous, if the note does not exist, or if the caller is not the note's owner. And so this is similar code logic to adding a user to the list of shared users for the note, but instead it's just going to be removing the user's principal from that list of principals that the note is shared with. Then we're going to define a delete note function. This is simply going to delete the note. It's going to use the same error handling as the previous functions, and it's just going to remove the note from the list of IDs that a user owns, and then it's going to make sure that it also gets removed from the list of users that the note is shared with. So it's not only removed from the owner's list of notes, but it's removed from the list of all users that the note was shared with. Then we have some definitions for the vetKD methods in the management canister. These are going to be called directly to the vetKD system API canister that we have deployed locally in the project, and it will not use the IC management canister that is deployed on the mainnet. And so within this vetKD functionality, we have a function for symmetric key verification key for note, and then encrypted symmetric key for note. And so these all do a variety of different encryption and decryption using that vetKD system API. And then we have a function for converting a NAT to a fixed size big endian byte or NAT8 array. And then we have some functions for upgrade hooks for the canister. So we have a pre-upgrade and a post-upgrade hook. And so that's going to wrap up this backend canister code. So if we go back to our tutorial here, we can also take a look at the files that are used for the application's front end. We have a couple image files that are used, and then we have some different framework files for Svelte, which is the framework that this front end is built in. So now to actually deploy and use this application, we want to start the local replica. So we'll do dfx start clean background. And we can see that I already have it running. If you get an error about communication with the replica, that's because in this project's dfx.json file, the project is trying to use port 8000, and this is a common local development port. And so if you get this connection refused error, you may have another process that is using this port 8000. So just be sure to kill that process while you are trying to deploy this application. Next, we want to deploy the internet identity canister. So we're going to dfx deploy internet identity, and then this canister needs to be initialized with an argument. For this, we're just going to initialize it with null. So we can see that now we have the internet identity canister running locally. And then we have the URL to go to the backend interface of the Internet Identity Canister, and we can also print this with the npm run command, but since we have it right here, we don't need to print it. And then next, we are going to deploy the vetKD system API canister. So recall that this canister uses the candid and wasm files that are stored locally in this example repository. And so we are going to do dfx canister create vetKD underscore system underscore API. And then for this, we want to specify a canister ID to be used for this canister since it is hard coded in the backend canister. So we want to use the flag specified ID, and then I'm just going to copy this canister ID to make sure that there are no typos. And I've got a couple new lines I also want to make sure I remove. And then that canister will get created locally, and then we need to deploy it with dfx deploy vetKD system API. And if you're curious, this canister is going to provide the system API that is described here. And you can learn more about this in the PR for this proposed system API. And remember that this feature is in development and it should not be used for production environments. So now let's deploy our backend canister. So dfx deploy encrypted notes Motoko. But you can also use the environment variable here. But for now, I'm just going to type that out. And we can see that my process got killed. So we'll just go ahead and rerun that. And now we can see we should have 3 canisters running: encrypted notes Motoko, internet identity, and vetKD system API. And then we also need to regenerate our canister interface binding. So we're going to do dfx generate and then encrypted notes Motoko. And we're going to see lots of type declaration files be regenerated. And so then lastly, we are going to deploy our front end canister. So dfx deploy, and that front end canister is called www. So we're going to do dfx deploy www. And we can see my process got killed again. So we'll just go ahead and rerun that command. So at this point, we should have 4 canisters running: the front end canister www, the encrypted notes Motoko backend canister, the internet identity backend canister, and the vetKD system API backend canister. So now to actually use this app, we're going to do npm run dev, and this is going to deploy our local development server, and we are going to have our local URL printed out for us here. By default, it should be port 3000, but we can see that I have port 3000 taken, so my system is using a random available port as an alternative, so that's fine. I'm going to open that in a new browser. And here we're going to see that we are met with this welcome page that prompts us to please log in to start writing notes. So we'll go ahead and log in. And here we can see the internet identity login screen. And so for this, we're just going to create a new local test internet identity. This internet identity should not be used with any production or real world assets. This is something purely for test only. And so we're just going to continue without passkey and just set up a quick PIN instead of going through the secure passkey configuration. And so we're just going to create this quickly for our testing purposes. And then now that we have our local test internet identity, we are logged in. And so we can create a simple hello world. We can add a tag for dev journey, and we can click add note, and we can see that it is being added. And we can also see the logs on the console here of the call to the canister. And then if we want to see all of our notes, we can go over to the menu and click your notes. We can see now we have hello world, and we can add other principals to allow them to edit the note. So for example, if we have another window here, and I just wanted to do DFX, who am I, or DFX identity, who am I, dev journey, and then DFX identity get principal. Here's my principal for this dev journey, and we can add this. And now we can see user added successfully. So now if I were to log in with that principal to this application, I would be able to edit the note. And we can go back to new notes, and we can say I love ICP, add dev journey as the tag, and then add the note. And so now we should have two of our notes, and we know that they are encrypted with the vetKeys system API. And so that's going to wrap things up for today's episode of the ICP Developer Journey. If you'd like to learn more about vetKeys, there are several resources linked in the documentation page for this example, including the vetKeys documentation, the technology overview, the discussion forum post, the primer, and also the research paper about vetKD. If you enjoyed today's video, please be sure to like and subscribe to the DFINITY YouTube channel and leave a comment below expressing your thoughts on today's video. If you have questions or got stuck somewhere, you can reach out to the ICP Developer Forum. There's a thread dedicated to the ICP Developer Journey where you can chat with other users who are also on their developer journey. Or you can also reach out in the ICP Developer Discord server, where there are tons of different channels for all sorts of different topics and areas of development. That'll wrap things up for today. Take care.